And so it's working on temporal cloaking and on manipulating entangled photon pairs by photons. So, Joseph, over to you. Come and tell us a little bit about yourself.
Thank you very much for that introduction. And I'd also like to thank all the people that made this moment possible for me. My advisor, Andrew Weiner, who unfortunately is on travel as well this week, so he couldn't make it today. And also my wife and 2 daughters couldn't make it as well. So I know she's very jealous that I get to experience London without her, but I'm sure we'll be back. And so they've been very important, my advisor in encouraging me and giving me freedom, and my wife in encouraging me and letting me work late a few nights and I'm getting too angry. And really kind of, my research got started maybe in unexpected ways. I think just as a researcher, I always like to say, what can I do? And then look for problems that really can take advantage of the capabilities that I have or the capabilities we have in our laboratory. And that's how it kind of evolved to get into these areas. When I started, my advisor didn't hire me to work on temporal cloaking or work on biphoton pulse shaping. It happened that we had these opportunities and we had the skills to really make a contribution, and so we pounced on it. And I really appreciate getting the chance to experience that in graduate school. And so really, the overarching theme of my research has been secure communications, a problem I think we all recognize as extremely important today. And I looked at areas that were a little bit more high risk, high reward type areas that are a little bit difficult to predict exactly how they will impact our lives immediately, but have the potential for a lot of improvements in down the road. And the first area was temporal cloaking. Now, this sounds probably weird. I mean, what the heck does that even mean?
It's Harry Potter, that's what it is.
But yeah, the idea is, if you can imagine a spatial cloak like Harry Potter, you put it on and no one can see you. Well, a temporal cloak says, well, if we can do this stuff in three-dimensional space, can we do it in time as well? And so in this idea, you would say, well, perhaps if you manipulated a light field in time, so you maybe sped up the front part, slowed down the back part, there'd be this region of space where if something were to happen, the light field couldn't detect it. And then you fill back in that hole and the observer gets this perfect unmodulated field at the output and says nothing happened, when in fact there was an event that actually occurred. And so this concept was introduced a few years ago, and it actually had an experimental demonstration in fiber optics in Alex Gaeta's group at Cornell University. But when we entered the field, we said, well, how can we make this practical in communications? So it's very cool to talk about these concepts, but can we actually make it happen at high data rates with real-world type data? And that's what we set out to do, and did manage to do a couple proof of principle experiments and actually hiding optical data with this idea of temporal cloaking. And so we're still a little uncertain exactly how it will make the most impact in the field. Ideally, we would like to do really big space-time cloaks and hide space for a certain point in time so you can run into a room and steal a painting. That was a picture that the news people really like to show. So we're very far from that point, so none of you have to worry about your paintings being stolen in that fashion. But it's at least interesting to think about what the future holds in that area. And the second one is built on an idea that by now is pretty well established, and that we can actually realize provable security using quantum states of light. So, but based on the idea that light actually comes in particles, and quantum mechanics, which says that if you do a measurement on that particle, you will alter it in some way that is irreversible. So if you have an eavesdropper in your system, they're going to mess something up that you can detect, and so you can know for sure if you're communicating securely. But despite all the great advances in this area, there's still a lot of roadblocks that have kept us from using it in everyday life. And one of them actually is speed. So in general, it's very difficult to realize quantum communication at high speeds. And motivated by that fact, a lot of people are looking into areas to get a lot of information from a single photon. And one way to do that is to look at time and frequency, areas that are very common in classical optical communications. We talk about wavelength division multiplexing, time division multiplexing. So these are fairly established classically, but a lot of the tools haven't been extended to the quantum regime. And so that's what we set out to do in our work, not really do a real quantum communication system, but manipulate these photons in ways that could be useful down the road in really making quantum key distribution a viable way to communicate, and one that really will be successful. So that's kind of the overall theme of my research. It's been a lot of fun. I mean, the fundamental reason I do it is just because it's so fun, and I just enjoy every minute of it. And so I thank you for the opportunity to come here and share some of that and enjoy being a part of the Marconi Society.
Thank you.
Thank you.